this, some of the strands of what we've been doing. So I want to say up front that a lot of what I'm going to be speaking about today relates to some joint work with Nate Broadus, who's at Ohio State, and Andy Putman at Notre Dame. But a lot of other people's work and some of their individual independent work is going to creep in here as well. So let's just, start by reminding ourselves what the context is. Like, we've been working hard this week. We've learned a lot. So let's just try to remember where we are in the landscape here. So our goal is to understand the cohomology of, depending on what set of mathematical structures you care most about, the cohomology of the mapping class group of a surface, or equivalently the cohomology of the moduli space of Riemann surfaces. So again, just to remind you what this P is, so all mapping class groups fix boundary components pointwise. The pure mapping class group will also fix marked points or punctures pointwise, okay? Right. And so one thing we talked a lot about in the first lecture is some work of Harrer that was all aimed at understanding the duality structure of the mapping class group. And so what Harrer showed, amongst other things, and I've been having trouble tracking down this reference. So this is referenced in Broadus's paper. I think that Ivanov did some of this independently in the case of the closed surface, but I haven't yet been able to find the original reference for this. So I can't confirm that, but I thought it was important to mention that. So in any case, we have this virtual duality structure for the mapping class group, and sorry, go ahead.
I'm so sorry, I will have to stop you because my computer just told me that in 15 minutes, without any other option, it will have to restart. And it's the one that is hosting and projecting onto the screen here.
That's fine. So what do you want me to do?
I will restart quickly and start with a different computer.
Okay.
Or wait, no, maybe I can actually give. Wait.
Start the different computer first.
Yes, start the different computer first. Very good idea.
It's amazing how these things happen live, right?
I've been warned earlier and I forgot to restart. It's entirely my mistake.
No worries at all.
My mistake.
It'll give everybody a chance to really commit to memory these numbers. Okay, that's everybody's job right now. There's going to be a pop quiz later.
Okay. Okay. I think it's okay. Oops. I didn't do that. Okay. Luckily, I'm recording with another computer, and that computer is now hosting. And I will try to just go out with the original computer, and hopefully everything works. If we crash for some reason, please come back immediately.
So far, everything just looks the same from where I'm sitting. So tell me if something is supposed to be happening.
Oh, and you can't hear me. Can you hear me now?
I can hear you now.
I want to have this as a speaker, and I want to have this as a microphone. Tara, can you hear me?
I can hear you, yeah.
All right, we can hear you again as well. And I should have paused this, but I think it's a funny thing for the recording, maybe. I think we are ready for you to continue. Thank you for your patience. I'm so sorry about that.
Not at all, that's not a problem. So it's okay to carry on?
Please.
Okay. So yeah, I was just reminding us, that we know that the mapping class group is a virtual duality group of a dimension that depends on the genus, the number of boundary components, and the number of marked points. This virtual bit is kind of important. I mean, what it means, I think, we've seen this a few times now, but there's torsion in the mapping class group in general, at least in the closed surface case. And so you're never going to be a duality group in the proper sense, but you're going to pass to a finite index subgroup that is torsion free and use that to get your duality structure. So it's those finite index subgroups that I actually want to talk a bit about today. And we'll get to that in due course. So, but again, this was all just like setting the landscape. We've all seen all this before, but the point of this slide is just to remind us that stable cohomology of mapping class groups or moduli space is well understood. And so I'm not going to say anything really about this. So Soren has been telling us about this. And so I'll refer you to him if you want to hear more. And we've already heard quite a bit about that. So the point is there, we have a pretty good understanding of what's going on, but in the unstable case, we don't know as much. Okay, so the good news for us is that there's lots, as I've said here. So the Euler characteristic is of moduli space is huge. This is a calculation that's due to Herrer and Zagier in the closed surface case, and building on that work, Bini and Herrer worked this out for the case of a surface with marked points. So that's good. We know that, if we persevere, we'll eventually be bound to find something, hopefully. But in terms of any actual classes, we know very, very little. So one thing we do know, and I guess this is going to be my get out of jail free card throughout the talk. I'll refer you to Soren. We've been hearing about this already. We have the one class, or the one family of classes that we know about comes from Chan, Glacius, and Payne. Okay, but in general, we just don't have a lot of concrete information here, and so this is what Andy and Nate and I wanted to delve into a little bit and see if we could try to understand this a little bit better. So again, so we've seen this result quoted a bit. So you might, the first thing you might try would be to look in the top dimension with rational coefficients, right? Because, what else are you going to do first? But Morita, Sakasai, and Suzuki, independently Church, Farb, and Putnam, proved that actually you don't see anything in this case, right? There's no information there. So, that's, I suppose, kind of unfortunate, but it's also very interesting. So what are you going to do next? Well, you might think, okay, we have these finite index, okay, so let me pause for a second. Let me back up. So you remember that the virtual cohomological dimension is, the max K, where there's some gamma module, some choice of coefficients where you get something non-zero, right? So just because we didn't see something with rational coefficients doesn't mean there's a contradiction in mathematics, okay? Now here, for the purpose of what is VCD, the finite index subgroup plays an intrinsic role here, right? That's the important part, because that's where we can actually measure cohomological dimension. You might think, so hang on a second, I might need another, let me see if I have room here. Might need another page. I'm going to insert a page here. So I should say that if you want to think about a similar result for punctured surfaces, so let's see here. Okay, so sorry, let me just give this a star. So this, I should say, is for the closed surface case. And you might think that something similar holds in the general case, but I should say that Chan has shown that this does not hold for S2n, at least for certain n. So you get some stuff in that case. But on the other hand, Andy and Nate and I have worked out some cases where you get zero again. So right now, I'm not going to state this as strongly as a conjecture, but maybe this is something to think about for the problem session later, which unfortunately I'm not going to be able to attend. But our guess is that if, okay, sorry, that's a badly written strongly greater than. If the genus is high with respect to the combined numbers of mark points and punctures, then what our calculations show seems to hint that we might find that this is enough to guarantee that you're getting you're getting zero with rational coefficients in your top homology. So, I mean, that's just sort of an interesting aside, but we don't really know exactly what's going to happen in that case. So that might be something people want to think about. Okay, so, right. So let me go back to these finite index subgroups then, because these play an important role in the theory of mapping class groups in general, not just in this particular strand where we're thinking about cohomology. But basically, we have these things that some people call the level L subgroups. This terminology comes out of algebraic geometry, where people refer to things called level L structures. They're also known as the congruent subgroups of the mapping class group. And what this is, basically, you're just looking at the kernel. So the mapping class group acts on the first homology of the surface, and we usually just mean with integer coefficients. But you can also just look at the action more generally on the first homology with coefficients in Z mod L. And one thing that's worth mentioning is when you are dealing with a closed surface, we saw this in a talk this morning, where we get the mapping class group, in fact, surjecting onto the symplectic group in that case. And well, I suppose it doesn't surject necessarily in general, but it maps into SP2G Z mod L. But the problem is that the intersection pairing is degenerate as soon as you get a combined number of boundary components and mark points of at least 2. And so in general, the mapping class group doesn't act via the symplectic group. Okay, so this is why I'm giving the definition the way I'm giving the definition. Okay, so one thing, you know, so these are the subgroups that we actually can concretely use when we were talking about virtual cohomological dimensions. So we pass to these finite index subgroups of the mapping class group. And as long as L is greater than or equal to 3, they are torsion free. And so this is something that we do all the time in mapping class group world, as we pass to these finite index subgroups and we say, okay, it's good enough to work there. So I guess one question for us that is the main topic of this talk is, you know, how much does that hold up if we're really interested in unstable cohomology? So in other words, you know, can we just pass to these finite index subgroups? So one thing to keep in mind, there's a theorem of, okay, this attribution is going to sound strange until I explain it. So let me write down the theorem and then I'll explain why I've attributed it that way. So in a certain stable range, the mapping class, the level L congruence group has isomorphic cohomology to the full mapping class group. Okay. And so the reason I've attributed it that way is that so Hayne did this for k equals 1 and n plus b less than or equal to 1. Andy had originally done this for k equals 2. So I won't write down the full conditions. I'll just write enough to indicate here. And n plus b also less than or equal to 1. And then Andy has proved it in full generality more recently. Okay.
And by full generality, you mean any kind of numbers of boundary components and mark points?
Yes, I should double check that after the talk, but I think that's right. Yes. Yeah, let me double check that after the talk, but I think so. Okay. Okay, so right. So the question is then, well, what happens in the topology? So again, what that's saying is that if you want to try to use congruence groups as a proxy for the full mapping class group, and if you're familiar with the Torelli group, you can think of these congruence groups as just sort of generalizations of Torelli groups. And, you know, in some ways they're not as nice because they're not the actual Torelli group. But they're nicer in the sense that they're finite index. But yeah, so it turns out things are very different in the top level. So once you get out of stability, these groups actually start to behave very differently. So here and throughout, I'm going to be thinking of V as the VCD. So this is a function, I just want to emphasize here, this is a function of G, B, and N. Okay, so what it turns out is we haven't been able to sort of construct actual classes, but what we can do is give bounds. And so for any level L, for any prime P dividing L, we get, I should say really these are lower bounds on the dimension of our top homology. So let me give some attributions here because this is not all entirely our work. So in the closed surface case, this was done by Neil Fullerton and Andy Putman. And I'm actually just going to give them the full attribution for this first line because really the case where n plus b equals 1 follows quite easily from what they did. And it's technically written down in our paper, but really I think the correct attribution there is to them. And this is my work with Nate and Andy. Okay. So, this is definitely one of those cases where, we're definitely, so I'm going to tell you about the proof of this theorem. And yeah, it's one of those cases where it's not entirely straightforward to go from the closed surface case to the case of surfaces with punctures and and boundary components. So there's some interesting new phenomenon that come up, and that's really what I want to talk to you about. So,
sorry.
Yeah.
Is the parentheses on the lower equation inside of the product? Does that mean you take that to the power of how many times you take the product, or is that outside of the product?
It's outside. So
okay.
So sorry, this should be like so. Okay. And I guess one thing that's good to emphasize here is that the Fullerton-Putman result is super exponential in the genus. And so you see an analogous result here in the general case. So this expression is super exponential in the genus, but also in the number of boundary components and the number of punctures. So in other words, it's a high lower bound. So yeah, one thing I really like about Andy and Neil's original paper is they write down what this is. It's some, for some low cases, just to impress upon you how big this number is. I don't have it in front of me. Oh wait, I do have it in front of me actually. Let's see if I can read it without my reading glasses on. No, I can't. But it's got a lot of digits. It's got like 15 digits once you even get to dimension 11 for the mapping class group of genus 4 in level 3, if that gives you any idea. So I can't possibly tell you what the digits actually are though, but I don't think it matters. Okay, so yeah, so I want to tell you how to find these bounds. And also just to tell you how we were able to apply some of the ideas that we've talked about earlier this week. So let's go back to the dualizing module. Right. So if we're trying to look at, so V again here is the VCD level, okay? So if we're trying to understand this, we can just try to dualize, right? So we know all about the Steinberg module now. And we know that through duality, we can just make this a question about zeroth homology with coefficients in the Steinberg module. Okay, so we're experts at this now. And this, sorry, should put that down here. And this just means that what we really need to understand is the co-invariance, right? So if we want to understand zeroth homology, we need to understand the co-invariance of our level L congruence group acting on Steinberg module. So, I mean, again, because this is a finite index subgroup of a virtual duality group, it has the same VCD and it has the same dualizing module as the full mapping class group. And our starting point for dealing with this is, we need to understand, and this motivated the simplification of Herer's proof that I was telling you about earlier in the week. We need to understand how the Steinberg module of a surface with n marked points relates to the Steinberg module of a surface with one fewer marked point. Now, there's a simplification that has to take place there. I've sort of swept boundary components under the rug for a moment. But basically, what we need to understand this is an analog of, some sort of Berman exact sequence. We need to be able to do induction is basically what it is, okay? And so, this is why we started looking at these inductive descriptions of how to build up the curve complexes in these cases to try to understand the spherical structure there. So yeah, that's sort of how we all got into this, basically. Okay, so luckily we've done that work, right? So just want to remind you, I'm using the notation from my previous talk that if I have the curve complex of SGN, then this decomposes as a join of the discrete set. So remember, these are arcs that join a point P to some other marked point on my surface. So it's the collection of all such, and we're taking the join of that with the curve complex with one fewer marked point. And so that tells me how to get started with computing this, doing these calculations that I want to do. So, so here, I just want to remind you, I'm trying to be consistent with my notation throughout these talks. So this M, this is the homotopy dimension. So maybe I'll just write that down. This is the homotopy dimension of the curve complex of SGN. Okay. And so the Steinberg module, by definition, is this reduced homology group. And that, maybe I'll just write this down. This is 2G minus 3 plus N. I hope that's right. You can check me on that. So, okay. Now I'm just going to go and try to compute this, okay, and see how far I get. So if I want to break this down, right, I'm just going to get out, my favorite version of Kunith, and what I'm going to get is the 0th reduced homology for AP with coefficients in Q, tensored with the M minus 1th reduced homology for the curve complex with one fewer boundary component. Okay. Okay. So then you say, right, well, we'll just keep that first factor for now, say something a little bit about that. And this, of course, is, just the Steinberg module. So really, I'm just convincing you of what I claimed already, that if I really want to, understand this, I needed to understand the relationship between the Steinberg module with n punctures and the Steinberg module with n-1 punctures. And this is what it is. And so let's just remind ourselves what this first factor in the tensor product is. So this is just, so I guess I really just secretly think of this as a copy of Q for every one of these arcs, but it's not really quite that. So, really what we're doing, okay, we all know homology in this group, but we're just, taking the kernel of the augmentation map here. So that's algebraically what this is. And we're tensoring it with this Steinberg module. Okay. So that's a good start. We're doing well here. And so I've been ignoring boundary components. So now I'm going to convince you that that's legitimate. Although I do want to keep track of them, but there is a simplification we can do. So let me show you about that. Okay, so I was kidding. I wasn't really going to give people a pop quiz on all of these formulas. I can barely keep them straight myself. So I've written them down here. So in the general case, this is our VCD. Okay. And what I want to do is compare that to the case where I have kind of shifted all my boundary components into punctures. And you can think of topologically maybe what's going on there as like filling in a disk. Okay, so in that case, you know, basically what I'm going to get is that I've lost B when I've done that process. Okay, so the only thing that's different here is a B summand is missing. I've got 2B in the first one and B in the second one. So, okay, so we've noted that. And so our first lemma is that if I take the top homology for the first group, the mapping class group for S, G, and B, actually I get something isomorphic to the top homology for S, G, N plus B marked points and no boundary components. Okay, but just notice here, this is important. These are not the same V, right? So we've shifted the dimension here. And this is true for all levels L and for all genus, okay? So again, I'm just gonna emphasize here, V equals V prime plus B, okay? So that's gonna be important for us, right? So yeah, don't need to remember any of the other stuff, just remember V equals V prime plus B, that's the important part, okay? So let's think about this. So I was just trying to move up my slides on my laptop instead of my iPad. I think that's that's a bad sign. So anyway, how do we prove this? How do we prove that I can make this simplification? So so we have this natural map. And again, you can think of this just from, you know, in the full mapping class group at first. So this is the sort of filling in a disk map. Okay. And so what is the kernel of this map? So I haven't passed to congruent subgroups yet, but the kernel of this map is, if you think about it, you're just basically Dane twisting around the boundary components. That's what you're losing here, right? So if you're familiar with Berman exact sequences, this is just you know, one of the instances of a Berman exact sequence. So you get a copy of the integers for every boundary component. Okay. And this is central because of the fact that it's generated by these twists around boundary components. Okay. And this kernel is contained in these congruent subgroups for every level because we're acting trivially on the homology. Right? So in other words, I get a surjection on the restriction to, so I get a map here, and I end up with a central extension. Let me just write this down. So I've got my kernel is just a bunch of copies of the integers, and I've got P mod S, G, and B. This gets to be a lot to write out, but it's all important. P mod S, G, N plus B, and I'm out of room, but luckily I'm on an iPad. Oops, I moved that word along. Okay. And yeah, oops, I left out the level. Okay. So, so I get this nice short exact sequence, right? And short exact sequences, we all know this is our bread and butter, right? This is what we live for. And in this case, what it means is I get to run a spectral sequence argument, right? So, so we now just get out our copy of, Hochschild-Serre spectral sequences for dummies, and we write down what we get on the E2 page. And so what do we get? Well, this is what we get. We get so we get our Pth cohomology here with with HQ coefficients, and since these are all nice, well-known groups, we end up just getting our little product here of a bunch of copies of Q. So that's all good. So let's focus on the first factor. Okay, so so what was the fact that we were supposed to recall from the previous slide or 2 slides ago? Pop quiz. So I won't actually ask you to remember the whole formula, but what was the key part? It's just
V equals V prime plus B.
Awesome. Thank you, Peter. Okay, so that was the easy part. So remember, this is the VCD in the sort of the SGNB case, and this is the VCD in the case where we had SGN plus B 0. Okay, so the only non-zero term that we're going to see here, maybe I should write some of this down instead of just saying this out loud. So the only non-zero term with P plus Q equals V prime plus B is kind of the one that you sort of feel like it should be, where P equals V prime and Q equals B, okay? So in other words, I'm gonna get E to V prime B. So I realize you could all just write this down yourselves, but it's probably helpful if I write it down. I'm going to stop writing zeros. I've already done that actually, just to keep this being less cluttered. Okay, and then I've still got this, oops, not to Q, this, all these
Wanted to write a
Q
B
factors.
instead of the Q.
Sorry?
A B instead of the Q.
Where did I write B? Oh, did I? Oh, I beg your pardon.
No, I'm saying you just wrote Q lambda or like exterior power of Q, but the Q should just be a B because you set Q to B.
Oh, thank you. Yes. Thank you. Thank you. Thank you. Yes. Yes. Okay. Yeah, I don't like having slides where everything's kind of written already because, it can be kind of visually off-putting, but like, on the other hand, I'm opening myself up to those kind of live typos. So thank you for keeping me honest. I appreciate that. Okay, so what do we get in this case? Well, that observation was exactly the key, because then that's just going to drop out for me. So, right, okay. So, so that's the result that I wanted to achieve. And well, I mean, so I guess there's a little bit more work to do. I mean, so you need to sort of observe that there aren't any non-zero differentials that can come out of or into this. So this is going to survive to the E infinity page, but basically we're done at this point. Okay. Okay. So, so that's all good. So we've made a major simplification here where we can really just, at very little cost, forget about boundary components for a bit. Okay. So, all right, what other simplifications can we do? So here's an easier theorem to prove. right? So this is not the, I'll restate the theorem we're trying to prove in a moment, but remember the whole point was we just got this like huge lower bound on the dimension of the top cohomology. That's what we're going for here. And so what this is going to, let us do an induction step, of course. So, okay, so I'm going to try to, in the time that we have left, I'm going to try to give you some of the key ideas that go into this proof and also tell you how to derive our main theorem from this easier theorem. Okay. So, okay, so first of all, let's just consider some kind of basic surfaces. Okay, so surface with one puncture and no boundary components, vice versa, or like no boundary components or punctures at all. Okay. And I've written down again for convenience because I didn't want to give a pop quiz what the VCDs are for each of these, right? And what we do here is just take us through sort of a basic calculation here. So yeah, this not sure what there is to say here. I mean, we're just kind of taking ourselves through. We've got just a basic homology calculation, and maybe in the interest of time, I won't spend too much time on this. We're using the same tricks that we had before. We're using our lemma, we're using duality, we're using co-invariance, and we get the result that we need in this case. Okay, so maybe I think just in the interest of time, this will be in the lecture notes and you can go back through and check that I've dotted my I's and crossed my T's here. But I think what I want to focus on is maybe the more interesting case. So if I have n plus b at least 2 and genus at least 1, then what happens here? Okay, so so I'm just thinking about the dimension here. So if I have my top cohomology for this group with this assumption, so by the lemma, I can simplify to the top dimension with all the boundaries shifted down to marked points. And by my easier theorem, so this is, yeah, so I should say I'm trying to derive our original theorem from the easier theorem. I should have said which of the two things I was actually trying to do. So, I can shift one down here, and I'm going to pick up this. I'm going to pick up this factor here in the front, and the cost of doing that is shifting the dimension. Now I'm being careful at how I'm shifting the dimension down by 1 here. And so you might find it useful to refer to this formula. So this is this quantity, take away 1. Maybe this is all clear, but I find I have to pay close attention when I'm keeping track of such things. And, all I have to do is just keep inducting, right? Or sorry, keep, reapplying the theorem over and over and over. And eventually what I'm going to get is this product that, that I was aiming for. So let me write this down. Looks something like this, missing a factor there. And this is just the dimension. And now I'm sort of back in these nice cases where I just have the one component, or the one marked point, I should say. I always run out of space for my coefficients. Okay. So, you know, it's yeah, so it's you know, the simplification is really what we want to do here. It follows pretty easily once I have that in place. So how do we prove the easier theorem? This is, you know, maybe where the hard part's going to be. So it's not so bad, actually. So, I mean, you know, so when you start working on these kinds of calculations, you realize you're just, you know, once you prove one or two key lemmas, you're really just using the same results over and over again and trying to get as much mileage out of them as you can. So again, we're starting with our top homology here for the surface SGN. And, you know, we convert this into thinking about zeroth homology through duality. And once we're at the zeroth level, then we're just looking at the Steinberg module. But okay, you know, we're looking at the Steinberg module with the congruence group acting on it, right? So what we want to do is, you know, so here we just have the congruence subgroup, you know, acting diagonally on this tensor product. And so on the first factor, it's pretty clear what's going on. You know, this is just a subgroup of the mapping class group, and we're thinking of these as just basically just generated by arcs in the surface. So the mapping class group is just permuting those arcs. Okay. The right-hand factor, we just need to be a little bit careful because, you know, I am trying to be careful about my indices here. I'll zoom in, right? We've got an n here and an n-1 here. So I'm just acting via the forgetful map, okay? And so this is why we're getting bounds and not precise numbers. So I can't tell you exactly what dimension this has, but what I can do for you is construct a surjection onto something where I can tell you what the dimension is, okay? So what we're surjecting onto, so I'm getting, you know, again, I'm just making use of the tensor product structure here. So on the right-hand side, I'm just getting the level L congruence group acting on the Steinberg module with one fewer marked point. And over here, what I'm actually doing is looking at not the set of arcs anymore as generating my vector space, but the set of arcs modulo the action of the level L mapping class group. Okay, so the question is, you know, how many orbits are there under that action? So we're almost done at this point, and I'm not sure how much more I want to say, but maybe I'll just say here that okay, so this part you can actually count, and so maybe the key fact, oops. Okay, so I will draw a picture here because it's sort of killing me to go through so many slides without drawing any pictures. So I have my arcs. So remember, my arcs look like this. So they go from the point that I want to forget to some other marked point, which maybe I'll call PK. So if my arc goes to PK, I'm gonna say that lives in the kth part of my set A sub P. And so this means that A sub P gives us a sort of useful disjoint collection of subsets. So we can see this is the disjoint union. of these arcs. And so a key fact that we're going to use is that, so I'm not going to prove this, but I think it's plausible anyway. If I look at the set of all homology classes, and this is why this is one of your exercises to show that there's sort of two different ways to define these level L congruence groups. This one is easier in this case. Well, I should say, sorry. So the boundary is just, Pn and Pk, or just P and Pk, sorry. Change notation there. So this set has L to the 2G elements. Okay. And so this is where that, so here's our easier theorem that we were trying to prove now. This is where this L to the 2G comes from in our bound. And then of course the n-1 just comes from the fact that there are n-1 of these subsets of my arc complex. So, hopefully that gives you at least some feeling for why this kind of result should hold. We're doing an induction argument. Let me just be 100% clear here. We're doing an induction argument, and at the end of the day, we're using Fullerton-Putman's result that you get this super exponential bound for the closed surface case. So we're using that in a very fundamental way. But we really had to sort of come to grips with this structure of the curve complex, the Steinberg module, and this sort of inductive way of thinking about them when you're dealing with the punctured case, which really, I think, like I said earlier in the week, I think this is all implicit in Herer's work, but it's not explicit. And I think in some ways it's kind of hard to extract from that paper, even though if you really delve in, it's the ideas are there. So I should say, so just wrapping up a little bit, we give two proofs of this result in our paper. And the one that I've shown you is my favorite. And I think it's because it I think illuminates the structure of these fundamental objects associated to the mapping class group and the way that you build them up inductively. And that gets used in a really fundamental way here. But I did want to mention that there's an alternate proof, which is in some sense more direct. And that uses a Berman exact sequence for congruence groups. So the first thing we have to do in this alternate proof is write down, prove a Berman exact sequence for level L congruence groups for a general mapping class group. That maybe is useful just to know that that's there in case anybody wants to think about that. But I guess a key point there is that also you need to understand the dualizing module for the fundamental group of a punctured surface and see how to identify it with these arc complexes, or not these arc complexes, but this collection of P arcs, as I've been calling them, and that enables you to go ahead and prove this. So basically, the structure of that proof is you write down this Berman exact sequence, And then you go through a similar spectral sequence argument with that short exact sequence, and out pops your bounds, basically. So you end up going through the same simplification that I outlined here. You prove this easier. I showed you how the main theorem derives from the easier theorem, and then you use the Berman exact sequence strategy to prove the easier theorem. So that easier theorem reduction is integral to both proofs. Okay, so that was really the first thing I wanted to say, just as a final remark here. The other thing that I wanted to say, I don't know how much interest there is in this for people at this conference, but there may be a certain amount. So I just wanted to mention that there are applications to the coherent cohomological dimension. So the coherent cohomological dimension of a variety, so let me just define it quickly. I guess it's sort of what you would expect it to be. So it's the max K where there's a sheaf such that I think you need a quasi-coherent sheaf. I won't write that down, F, so that the kth cohomology of your variety with coefficients in F gives you something non-trivial. So it's just an analogous definition for cohomological dimension for a group. And it's a measure of geometric complexity of your variety. So one thing that you get out of this, this piece of work, is you get bounds. So I won't write this down exactly just for lack of time, but one corollary that you can get from our work here, and I think this was part of Andy's original motivation for thinking about this, is you get bounds on the coherent cohomological dimension of the moduli space of a surface with marked points. And one thing that's interesting about it, so I'll just mention this because I think this is something I don't feel like I quite I don't know, fully have a good feeling for why this should be so. But it turns out that your cohomological dimension actually just is bounded by the cohomological dimension of the closed surface case. So all of the bounds that we get for the surface with marked points are actually independent of the number of marked points, which seems a bit strange, considering that structure really does make a difference. I mean, you're getting these super exponential bounds, on your homology. So somehow the punctures aren't playing a role when you're talking about this kind of cohomological dimension. So I realize I'm saying that a bit vaguely. But it's something that may be of interest. I just wanted to flag that for people. So that's all I wanted to say about congruence groups. But if I'm allowed to steal 2 more minutes, since I had to pause for a second, I might claim 2 minutes. Is that okay, Peter?
Oh yeah, absolutely. Yeah.
So since I can't go to the problem session later, I thought it might be interesting to flag some open questions. And they're not actually my open questions, they're Nate Broaddus's, but so they go back to more what I was talking about on Tuesday. I mean, I flagged some areas at the beginning of this talk where there are some interesting questions, I think, about what happens with rational coefficients and things like that. So those are things people might want to think about. And I did want to say that in Nate's paper, so the paper that was the focus of our attention on Tuesday in my lecture is Nate's Duke paper on the Steinberg module for mapping class groups. And he has a section at the end. So Nate's paper has a section, and I forget what it's called, but it's something like further questions. And there's lots of good stuff in there. And most of them relate to differences between the closed surface case versus the once punctured case. So we spent most of our time talking about the once punctured case. And, to roughly summarize what we said on Tuesday, we said, you get a lot of results for the closed surface case, but there are some differences along the way. And there are some things that actually are still a little bit unsettled in the closed surface case. So most of Nate's questions relate to that. He also raises the question of what is the right notion of the dualizing module for out FN. I think we've covered that well so far this week, so I won't say any more about that, and I'll refer you to Jeremy there. But there's one thing in Nate's paper that I think people overlook because it's not in the further questions section, and this is what I really just wanted to mention. So this is at the end of section 4.2. And so if you want to find this, I wanted to write down the reference so you could go and look at it. But basically, as a consequence of Nate's generation results, that there exists a left ideal, which he calls J. I'll try to use his notation, that sits inside of Z mod SG, which is surjecting onto the Steinberg module in the closed surface case. And one question that Broadus raises is a geometric interpretation of J. So there's this algebraic description of it. We have this exact sequence, but there isn't, at least that I'm aware of, and I did ask Nate Broadus last week if he knew if somebody had given some of this. So it's possible that somebody has done this and we're not aware of it, but I haven't seen any sort of nice geometric interpretation here. And the other question that he raises here is, so we have this generator, which we constructed last time, this Broadus sphere, which actually we were thinking of as a filling system in the arc complex at mod the arc complex at infinity. So this was our generator, and what is its stabilizer in the mapping class group, the closed surface? It sort of is what it is. That I've just described it, but is there some sort of nicer description of it? And Nate gives a little bit more discussion in his paper of why this is an interesting question. So so I'm gonna end there, but I just wanted to flag these because you can find the section on further questions without me having to point you to it, I'm sure. But these two questions I think are really interesting, and sometimes they can get missed because they're tucked in at the end of this section. So I wanted to call your attention to that, like I said, since I can't attend the problem session later. So anyway, thank you. I'll stop there.
Yes, maybe we'll start again with Zoom. Are there any questions on Zoom? If that is not the case, are there any questions here? Vignesh? Should I come there? Yeah, either that or I have to rephrase it and probably butcher what you're saying. Yeah, come please.
I don't. is there any like natural surjection from this unmarked moduli space to marked moduli space? You were mentioning this bound of coherent, the cohomological dimension. So do you have any surjection from the unmarked points to the marked point?
So no is the short answer. So no, we don't get a surjection in that case. The surjections generally go the other way. So are you asking like how we get these bounds? Is that?
Yeah, if we have a surjection, we usually have a bound of cohomological dimensions.
Yeah, so maybe I opened a can of worms here. I mean, it's a little bit yeah, it's a little bit yeah, maybe it's something we can talk about in the exercise session, because I'd have to say a little bit more. But I guess one thing I should say here is that there's a conjecture of Huyenga that so this is probably worth mentioning. So this result here, and I don't know why I put the parentheses in the wrong place. There we go. So Huyenga's conjecture is that this is always greater than or equal to G minus 2. And it's been proved for G up to 5 by Fontanari and Pascaluti. So yeah, I guess, yeah, so maybe I'll stop there, but I'd be happy to say a little bit more during the exercises, because it's a little bit involved to say where the bound comes from.
Okay, thank you.
Yep.
Other questions? Yeah, Andrea.
So in the theorem that you wrote at the beginning, there was also a choice of a prime P dividing L.
Yeah.
I remember, but then
And then it disappeared. Is that your question?
So where does it?
So why is it not here in the easier theorem? But let me go back to the original statement.
How, if you can say a few words on how this choice of prime affects the estimate.
I'm really glad you asked that. Because I meant to say this. So this is where Fullerton-Putman come into play. So basically, the argument that I showed you for to how to obtain the result for a general surface, basically you're inducting down until you get to a closed surface, and then you invoke Fullerton-Putman. And what Fullerton-Putman did was they construct, in the case of the closed surface, they construct surjections onto linear groups over a finite field with P elements. And that's where the P comes into play. So really it's you know, in what we do, P basically doesn't play a role except where we invoke that. So thank you for asking that.
Are there other questions? Well, if that's not the case, let's thank Theorem.